Okay, so let's have a look at question number 4. We saw that from last tutorial, S4 of t, which is expressed by exponential of 2t, was hard work trying to find the trigonometric Fourier series for this particular signal. But we're going to see that if we were to use the complex exponential Fourier series to break this signal down, it becomes significantly less work. Okay, so basically now we're going to go ahead and finish this question, and then of course we're going to check it with MATLAB. Okay, so here we go. So Fourier series, let's start with the definition first. J2 pi n f naught t, and our Cn coefficients are calculated through this integral. 2 pi n f naught t dt. Okay, so the things that we need are t and, of course, f naught. Okay, so let's look at that first and see what we have. Okay, so it's periodic with the interval between 0 to 1, so its period is 1. So we can go period is 1, so of course its reciprocal is also going to be 1. Okay, so this should make our calculation a lot easier. All right, and then of course our S of t was e to the 2t. Okay, so let's go ahead with this integration. And last week you would have seen, yeah, if you did this through the trigonometric series, it's not a nice integral to deal with. Okay, so e to the x will do just fine here. All right, so integral between 0 to 1, because our t is equal to 1, e to the 2t, e to the negative j 2 pi n, f naught is equal to 1, so I leave it out, dt. Okay, so having this sort of expression, I can simplify by basically adding the indices. Okay, so indices will add, I should say. Okay, so it's between 0 to 1. This becomes 2t 1 minus j pi n dt. So this becomes significantly easier to integrate. Okay, e to the x still goes to e to the x. So it becomes e to the 2t 1 minus j pi n. And of course, we divide that by the derivative of the inside. So we divide this with respect to t, and that ends up with this coefficient here. And that's it. Significantly easier. Okay, so don't forget your upper and lower limits. Now we simply plug those values in. Okay, so good idea, factorize. Okay, and now upper limit minus the lower limit. So I have here e to the 2, 1 minus j pi n, substituting 1 inside, minus e to the 0, disappears, just 1. Okay, so basically that's it. That's the final expression for your exponential Fourier series. Now, you could argue we could probably take this a little bit further and say, what happens if we were to expand this? Okay, so for instance, here we can go e2, e to the negative j2 pi n. So this is the multiply here, minus 1. Okay, so you could argue that this is essentially, okay, so this is magnitude of 1, or if you just consider this is magnitude of 1, if you like. Okay, and it's going through a clockwise rotation, okay, of integer multiples of 2 pi. So it always ends up at 1, basically. So irrespective, we could probably get rid of this and say this is multiplied by 1. Okay, so I can probably simplify further just to say this. Okay, and that's all. This is your Cn coefficient. But on top of that, it's probably a good idea to work out what C0 is. Okay, this is the average value. Okay, so integrating this, e to the 2t on 2, between 0 to 1. Okay, so that'll give you e squared on 2 minus a half. Okay, so it's significantly easier to do. And that's great. Okay, so let's go over here. I prepared some MATLAB code just to see what it would look like. Okay, so in this case, I set it to be set it to 120 coefficient. Let's just stick with 3 for now. Okay, stick with 3 for now and just run that bit. Okay, so it might not look like it at first. So this is your either the 2t function given in red, and the blue function up here, this is your approximate. So it might not look like it yet. Okay, but as soon as I crank this up, so let's go 30 coefficients. As soon as I do that, it should look better and better. Okay, and this is, of course, this is over one period. So between 0 to 1, it looks pretty good. And of course, if I go to 120 like I had before, it'll be even better. Okay, so that looks good. Now, I also, in lines 149 to 151, I also went ahead and converted my complex exponential coefficients into the trigonometric equivalents. Okay, so that was basically done here. All right. And I've used that to go on ahead and basically generated the trigonometric Fourier series equivalent. Okay, so as you can see, these two are exactly the same. Okay, so complex exponentials is significantly less work.